Hi there, welcome to the CobBauge building. My name is Dr. Matthew Fox from Fox Ecological Architects at Plymouth University. I'm here to talk to you about the CobBauge building that we have here at Plymouth University. I'm just going to show you around the building and talk to you about some of the different materials, the different components, and some of the things that we're monitoring as part of this research project. Come on in. Here we are inside the CobBauge building. It's a relatively small space. It's a single room classroom. It's also a live lab test facility, so we'll be doing lots of monitoring. I'll talk to you about some of those bits and pieces as I go around the building. Yeah, it's kind of nicely formed, concise, small little building. Okay, so as we were designing this building, although the main emphasis has been on producing a building that could demonstrate and showcase the CobBauge material, we're also really keen to use materials that had an inherent low embodied energy. And a lot of time and effort was spent trying to develop details that work with materials with a low embodied energy. So, for example, in the foundation, we were using a high PFA content concrete. It would be really nice in the future, and maybe for some of you designing future CobBauge buildings, to try and even eliminate the concrete from the foundation. But for our engineer at the time, concrete was what we had to go with. So we decided to go for as low an embodied energy concrete as we could possibly get away with, and it was a high PFA content to that. We then used, to minimise cold bridging, foam glass insulation as a moisture resilient insulation material between the cavity of the external brick and the internal low density concrete blocks. Again, low concrete blocks, not necessarily the greatest, but sourced to give the thermal properties whilst maintaining the structural performance of the wall, of the plinth to support the CobBauge walling. In the ground floor here, we have about 200–250 millimetres of foam glass insulation below 100 millimetre high PFA concrete screed. And then on top of that screed slab, we've got the slate flooring that you see here. So again, using an insulation that is a low embodied energy and is kind of working to kind of help give a high performance to this building. Then as we work up, we have the CobBauge walling. So the CobBauge walling starts about 400 millimetres off the floor. So it's 400 millimetres from the external ground level. And then we have the CobBauge rising up. This building was built in a series of 5 lifts. Each lift was about 600 millimetres high. So we were working our way up through the build process as we went. And once we completed the walls, we left them to dry for a good period of time. One of the key factors when building, or even in fact when designing and planning out a CobBauge building, is to allow sufficient time for the cob to dry out. So we finished all of the cob walling towards the end of October, sort of mid to late October in 2021. We then left that to overwinter, so it was gradually drying out. It's not ideal to kind of let it overwinter. It's more ideal to kind of let it dry out over the sort of warmer periods of the year. Sorry. But anyway, this was the position that we were in with the Plymouth University timetabling. So we left it to overwinter, and we then came back in April, and we started to apply the internal clay plaster finish and the external lime render finish. So this is a clay plaster finish. It's applied directly to the CobBauge surface, and that's the structural layer. And there's not really very much to it, really. What we noticed was when we applied the clay plaster to the CobBauge walling, the walls suddenly stopped drying out. So we were monitoring the moisture content through the thickness of the walls, and that moisture content, the degradation of that moisture content suddenly slowed down because you're applying what is inherently a very wet clay material to what is already quite a moist clay subsoil material in the CobBauge walling. So that took quite a while to sort of dry out, and it also meant that these clay, the clay plaster also took quite a while to dry out as well. So much longer than on a traditional building. In the ceiling here, so obviously there's no cob up in the roof space, but I'll just talk you briefly through the roof construction. So on the top we have zinc standing seam roofing, and that's on a sarking board deck. Below that sarking board deck is a 50mm vented cavity. Then we're down to the rafters, so we've got some quite chunky rafters in here. Between the rafters is full fill sheep's wool insulation. And then below the rafters on the sort of inner side, we have about 80mm of rigid wood fibre insulation to minimise the cold bridging through the rafters. Fixed to that is Smart Ply Pro Passive, which is a kind of a high performance airtight OSB board. So that's applied to the underside of the rigid wood fibre insulation. We then decided, because the university have got lots of building services, to run most of our building services through the ceiling. So we've allowed for a 75mm service cavity in the ceiling, and that's just spaced by timber battens and allows all of the services to get up into the ceiling. The services then branch from the ceiling down through cavities within the wall. So these were chased out after the building was completed. So the builder then came along and gouged out chasing runs for the services to run down, and we've got these sockets here. That's how we decided to deal with the services on this building. And a slightly different example is over here. So for the IT and audiovisual facilities and services that are required for the university, they decided to run them through this plastic conduit or trunking area. Not ideal because of all the plastic and the embodied energy that goes into that. You might, in future projects, think of alternative materials. But this served as an alternative way in which you might get building services down. Rather than chasing them into the walls, you could perhaps do some surface fixings and run them. Maybe you could run your building services around the wall in sort of higher or mid-level dado trunking areas. So this is another way of doing it. But just turning your attention back to the ceiling, to sort of finish off the ceiling, we went for a Troll Tech wood wall board, and that gives acoustic properties, has a relatively low embodied energy content within the actual material itself. It also makes it quite easy if the university want to come in and start taking down panels to access services. So as a sort of a maintenance aspect, this material, this product worked really well for the university. Okay, so building services throughout this building are really minimal. We've got an electric heater, which we chose for this particular building because we wanted to try and isolate the heating source. And by going for an electric point of heating, we can monitor the amount of energy that's being used over the prolonged period of time. We can isolate that from the lighting and from other activities and services that are ongoing throughout this building. And we can then start to work out how much energy per square metre per year a CobBauge building such as this might use. So it's really interesting and useful data going forwards. For the lighting, we're using very high-tech circadian rhythm lighting systems here. So these lights are tuned to the external lighting as well, so they will adapt depending on the external lighting levels and lighting conditions. We also have a specialist control panel over here, which can change the colour temperature of the lights. So as part of this facility, which is within the University of Plymouth campus, it's also important that we were going to use this space as a training facility for our students. So we're going to be able to teach them some of the underlying building physics, not only with the building fabric, but also with the lighting, with acoustics, with air tightness and all sorts of other different aspects that go into a general building. Okay, so as this is the first prototype CobBauge building in the UK, we decided that it's really important to use this as an opportunity to monitor the heck out of it. Monitoring will take place throughout the lifespan of this building, but it was also important to try and start that monitoring process during the construction phase as well. And for that, one of the most critical aspects of a CobBauge wall is to understand the drying rate and the shrinkage rate, the combination between the drying and the shrinkage. So over here, if I draw your attention, we have a box of data logging equipment. That all connects through to sensors that are embedded in the wall. So we have a series of about 8 moisture monitoring sensors that are buried at different lift heights and different locations within this wall, and they go through the full thickness of the wall. So we can start to work out or start to visualize through the data how long it takes for certain sections of a CobBauge wall to dry out. And we can then from that information infer how long it takes for, say, the core of the wall to dry out compared with the outer edges of the wall. How long does the structural element take to dry out? How long does the thermal element take to dry out? What are the impacts of applying a clay plaster or a lime render, and the ongoing implications of that? So we've got these sensors in place, and as I said, they will be monitoring for the next number of years, indefinitely, as long as they can survive. They'll be giving us information not only on the drying rate of the building once it's complete, but also the way in which this building will regulate moisture over its lifetime. So as we breathe and exhale, there's moisture that's accumulated within the atmosphere. How does a CobBauge wall, or how does a CobBauge building deal with that moisture? And that will be monitored through those sensors. Also on those sensors, we've got temperature profiles as well. So we can start to profile the temperature or the temperature difference through the wall thickness. So we can start to understand at what point through a wall does the temperature change, and relate that back to some of our U-value measurements, both through desktop calculations and also in situ U-value measurements using heat flux sensors, which will be starting this winter. Over in this location here, we have a series of protometer devices. These protometers are connected to a number of woodblock sensors that are buried within the wall. In the same way that our sort of sophisticated moisture sensors are doing, we've got very basic or simple woodblock sensors. And as part of our research, we're looking to try and understand how the woodblock sensors and the protometers, as a very low-cost solution, compare against a very high-cost solution of the data loggers we have in the corner over here. So these are multiple thousands. This setup over here could be a couple of £100. And the opportunity to perhaps use this as a technology going forwards on future CobBauge buildings to inform designers and builders on the drying times and the drying rates of their CobBauge buildings in the future. Other aspects that we'll be monitoring over the duration of this building. Over here we have indoor air quality. So that will be monitoring particulate matter. So we've got PM 2.5, PM5, PM10. We have VOC monitoring. We have CO2 monitoring, relative humidity, internal temperature monitoring. So we can start to understand the atmosphere and the thermal quality and how people respond within a space, and relate that back to the data. Outside, we have weather stations, we have external air quality sensors, so we can do a benchmark between the different sets of data. We have a series of thermal imaging surveys planned to try and understand where there might be cold bridging or other potential defects from this building. We're not anticipating that there are very many thermal defects. We had a good close eye over this building as we were constructing it. But it'd be really interesting to see it in the thermal world. Well, obviously we have to wait into the winter until we can start looking at that. We undertook an air tightness test on this building. The air tightness test was really good. For this building, although we paid attention to the air tightness, the ventilation that we've got through the triple glazed windows is only by opening them and by trickle vents. There's no mechanical ventilation in it, and a decision was taken early on to not explore the use of mechanical ventilation or mechanical ventilation with heat recovery. That may well be something for a future project. But the air tightness test came back and we were getting about 4 meters cubed per hour per meter squared, which is less than the building regulations for this commercial building, which would be 5 meters cubed per hour per meter squared. So we're within the building regulations, but we're not too airtight, whereby we would be starting to get nervous about not having any mechanical ventilation. The purpose of all of this monitoring, well, we need to demonstrate that a CobBauge building not only complies with the building regulations, but exceeds it as well. And we need to demonstrate that you can build a CobBauge building and the performance levels give you a really nice internal thermal comfort. Part of this was demonstrated during the summer. So during the heat, the high heats where we were getting 40 degrees plus external air temperature, outside, inside here we were at least 10. At some point we were 12 degrees cooler than it was outside. So vastly different and much cooler. This is where all the builders wanted to hang out during the summer. No one wanted to work outside. So already this building is starting to demonstrate and to sort of prove its credentials through summertime cooling. We're really looking forward to sort of seeing how this building performs over the winter.
Okay, ladies and gentlemen, this is an ad hoc video. Here we have Steve Goodhue, Matt Fox and Brian Murphy, and myself, Jim Carfrae. We are standing in Kirkby Lodge, where we feel relatively cool compared to the outside temperature. But we're now going to walk across from Kirkby Lodge through the blazing sunshine of one of the hottest days of the year into the CobBauge prototype building, just to see if we can clearly, just by experiencing the difference in temperature. So if you'd like to follow me. So we can immediately feel the effects of the sunshine, and it's the middle of the day. So there's a bit of a heat island effect, probably because of all the hard surfaces around. We're now walking through the landscaping works towards the front door of the wonderful prototype.
So what's it like
building
just here? That's warm.
Yes, is that an official measurement?
Yeah, this is an official measurement.
It's blooming hot.
It's blooming hot. It really is.
So we're now just going to see whether you feel the immediate effect of the thermal regulation provided by this wall system.
Oh wow! Yeah. I think I want my meeting in here, not out. Yeah.
Absolutely. So gentlemen, what are you experiencing now?
I'm having to acclimatise to how cool it is in here.
Oh, lovely.
Yeah, it is. Yes, it's exactly the same as me.
You'd imagine there was some sort of climate control in here.
Yeah. Yeah. Yes.
Right. And it is appreciably cooler than Kirkby Lodge, which in itself was not uncomfortably hot.
Okay.
But there's not the harshness of a climate control system in here.
No.
It's not that chill, and it's even. It's an even kind of feeling, and the door's open.
There you go.
Yes.
External air temperature just measured 35 degrees. Internal air temperature 25 degrees.
10 degrees.
10 degree difference.
Right.
And the door open.
The door's open.
Thank you, everyone. I am drawing this video to a close. That was a triumph of reality over expectation.
Okay, so now we're outside the CobBauge building. I'd just like to point you in the direction of a couple of materials. So on the outside of the thermal layer, we've gone for a lime render finish. This has got a through colour to it. So there's minimal work once the lime render has been applied. down below here, as with all cob buildings, you need a good plinth. So we've got a brick-faced plinth here, the DPC in at about 200mm. This comes up to about 400mm high, on which then the CobBauge material sits. So that's the plinth there. Another useful design tip is to have a good eaves overhang. So if you just pan up to here, we've got the large eaves overhang, and that's there to protect the heads of the cob walling. So it's to protect it from excessive rainwater. So that's there. We've got a good eaves overhang all the way around. It's a mono-pitched roof. Around the back of the building, we've just got the single gutter and downpipe. We do have a curve around the back, which we can go and have a look at in a moment. But I'd just like to also point out these windows. So we went for timber framed, triple glazed windows with an aluminium sill. And you can see how we had these plastic upstands, so we could feather in the lime render over the top to create a waterproof seal. In the corners here, we've gone for a linseed putty as a junction bead between the lime render and the timber frame windows. So that can be replaced, and it just makes maintaining these windows a little bit easier. At the head here, we've got a bell cast. Again, heavens forbid, because we've got the large eaves overhang, but if we had any rainwater on the face of this building, the bell cast's in place just to shed that water and to make it kind of easier to get rid of the water from the face of the wall. So let's go and have a look around the back and see this curve. Okay, so we're now around the back of the building, and we've decided as a design feature to try and include a curve. So whilst contemporary architectural styling these days is for sharp, crisp edges, and that's fine, we've demonstrated that as part of this building. Other design aesthetics and other people prefer or quite like the idea of including a curve as part of their design. You find this quite typical with other cob buildings, and we thought, well, we should at least demonstrate the ability to perform a curve. And that's what we have here, and it was very successful. Managed to create the curve very nicely. Up here you can see the wall plate protruding. So a very chunky piece of timber. It was sized as such because of the curve in order to be able to support the roof trusses and to prevent risk from wind uplift. So you've got quite a large piece of timber here, and that goes all the way through the building. And you have another one up here, a much smaller wall plate at the front.